Number 6 says the complete combustion of 2 moles of liquid benzene, C6H6, in oxygen liberates 3268 kilojoules of heat. It first asks us to write the thermochemical equation for the combustion of benzene. So all this is really writing the chemical reaction with the delta H value. So C6H6 plus oxygen gas gives us carbon dioxide and water. And then it gives us our delta H value. It says that every time we burn 2 moles of liquid benzene, it gives us this many kilojoules of heat. And I assume that when we balance the reaction, there will be a 2 in front of the benzene. So we will have to balance and make sure of that. 3268 kilojoules. Now this is combustion, so I know that this is going to be an exothermic process. It also tells me that it liberates heat, which means that it's giving off heat to the surroundings. So this is a negative delta H value. We do need a balance. So first I'll balance carbon by putting a 6 in front of CO2. Then I'll try and balance hydrogen by putting a 3 in front of H2O. That is going to give me an odd number of oxygens, however, so I'm going to go ahead back and I'm going to double these values. 6 times 2 gives me 12, and then 3 times 2 gives me 6, and then I will also double this value here. 2 moles of liquid benzene, which is what we wanted. So 2 times 6 gives me 12 carbons, 12 carbons, 2 times 6 gives me 12 hydrogens, 12 hydrogens, and now we just have to balance out our oxygen. So we have 2 times 12, 24, plus 6 more, so that's 30 oxygens, so I need to put a 15 in front of my O2 to balance out my thermochemical equation. And now that I have this balanced, I do indeed have 2 moles of benzene, which is good because it tells me that for the combustion of 2 moles of benzene, it produces this amount of heat energy. So A is finished. We wrote our thermochemical equation. Now B says, is the reaction endothermic or exothermic? And of course, because we have a negative delta H, heat's being liberated, so this is an exothermic reaction. Part C says how much heat will be released when 10 grams of benzene is burned. So we're going to have to do some stoichiometry here. So we start with 10 grams of C6H6. And I did not show sig figs correctly here, so we'll need to go back up and look at the given value in the end and round to 3 sig figs. We're going from grams to moles. And 1 mole of benzene, C6H6, 6 times 12 plus 6 gives me a mass of about 72.12 grams per mole, if we use the exact masses. And now we need to convert from moles of benzene, C6H6, into kilojoules. And so we know that our enthalpy value is stoichiometrically equivalent to all of the amounts in our equation. So for every 2 moles of benzene, we get negative 3268 kilojoules of heat. Alright, and so how much heat will be released? Well, we just need to solve this problem now. So 10 divided by 72.12 divided by 2 times 3268. So let's type that into our calculator. 10 divided by 72.12. Whoops. 10 divided by 72.12. Made a mistake that first time. Divided by 2 times 3268 negative gives me, got a different answer. I think I typed something in wrong. Let's try one more time. 10 divided by 78.12 divided by 2 times 3268. Ah, yes, I think I typed something in wrong the first time, so I got negative 209.16538. Sometimes if you think you have a mistake, it's best just to type it back into your calculator again. And I do need to round to just 3 significant figures here to match the 3 that I started with, so I will round to negative 209 kilojoules. So there is part C. And we can also outline this in green so it's clear that it's the answer to part C. Last but not least, in part D, it says what mass of benzene must be burned to produce 1 kilojoule of heat. So we're kind of just going the other way here. So still dimensional analysis, but this time we're starting with 1.00 kilojoules. And we want to know what mass or how many grams of benzene we have to burn. So we're using our conversion factors the other way. We'll first go from kilojoules to moles of C6H6, flipping our conversion factors. And then once we have moles, we can go from moles to grams. And that will give us our mass of benzene needed to burn. So looking back at our equation, we have 2 moles of C6H6 producing negative 3268 kilojoules. And then we already calculated out the molar mass here. We know that 1 mole of benzene is 78.12 grams approximately. So then when we multiply this out, we'll do 1 divided by 3268. So right away we know that this is not going to be a very large amount of benzene because we're only producing 1 kilojoule of heat, times 2 times 78.12. So I got a pretty small number here. I got 0.047809, and we do need to round to 3 significant figures here. And so our final answer would be rounded to 0.0, and those aren't significant, so I keep 3 more, 478. And this is our number of grams of C6H6. And it is important that you have unit and substance correct on your answer, even if you left off the substance in your dimensional analysis. So there is our final answer. We only need less than a mole, or less than a gram of benzene to produce 1 kilojoule of energy.